Hello students, Guillaume here with another R video. In this video, we revisit some of the concepts we've learned in previous videos, and we put them together to solve a slightly harder problem. In particular, we are going to use again custom functions that we create ourselves. We're going to use random simulations, and we're going to use the for loop to repeat an operation many, many times. Now, as a note, I recorded this video last year, and mostly here it's going to be the recording from last year. But this small part is the very beginning, where for some reason last year the audio was very bad just for the first few minutes. So I'm re-recording those very first few minutes. But then don't be surprised if my appearance changes slightly, because you're going to see me from the past. Now, what are we trying to do here is simply solve a financial maths or investment problem with R. And it's a problem we're familiar with because it's from the tutorial week 6 set of problems. So we solved this problem before with Excel simulations, and now we solve it again with R. And I think this highlights some strengths of R versus Excel, which is essentially we don't need a lot of space to solve this problem. In Excel, simulations require a lot of space because we need thousands of lines for thousands of simulations, and then also many, many columns. In R, it's just going to be a few lines of code to solve this, and it's also quicker. We can do many hundreds of thousands, probably millions of simulations, and it doesn't take long. So anyway, let me just review quickly the problem, and then we solve it in R. Okay, I'll share the screen. So this is, at least in 2024, question 2 in the week 6 tutorial on week 6. In this problem, we have yearly investment returns that are normally distributed. In the case of option A, there's a 3% mean return and 5% standard deviation. And in the case of option B, we have 5% mean and 10% standard deviation. Now, the investor invests 1,000 in those products at the beginning of every year for 30 years. And what we're very interested in is the accumulated value after 30 years, which we call big S. So that's, in essence, what we're trying to find, the distribution, the probability distribution of this S, which is the accumulated value in 30 years. And again, we use simulations to do this. On a timeline, the situation looks something like this. So first time is 0, and then the last time is 30. Now, those things called factor 30 and etc., don't worry about them for now. This is something we need in the code that I'll explain in a few moments in the code. But the situation, to make it clear, is that we invest 1,000 initially at time 0, but then again another 1,000 at time 1, and another 1,000 somewhere here at time 2 for 30 years. So the very last 1,000 that we invest is at time 29, but then we're interested in the accumulated value here at time 30. So what we want is this S, accumulated value after 30 years. Obviously, the returns in every year are random. So in one given situation, where you're going to obtain one value for S, another simulation, because of random variation, you'll get a different result, and then another simulation, blah, blah, blah. You do that many, many times to get an approximate distribution for this big S. Now, the general strategy is that we do this one time for one simulation. We simulate 30 years of returns. We find the value at the end of 30 years, S. That's one simulation. But with a for loop, we can do that many, many times, because a for loop allows you to do the same operation a set number of times. So we will go now to Guillaume from the past, who's going to explain this in R. I just recommend you to do it. Try to actually do it, because listening, maybe it sounds easy enough, but if you actually type the commands and try to follow and write the actual code as I explain it, I think you'll learn a bit more, and maybe you need once in a while to pause the video to make sure you do everything as I explained. And so yes, I leave you to a slightly younger Guillaume now. Let's do that in a function, okay? Because if we do that in a function, then we can just call our function 10,000 times or however many simulations we need. So it kind of makes sense here to do the first task, which is to generate 30 years of returns one time. It makes sense to do it in a function. So the function here, I'm going to call it ACC value, okay, just for accumulated value. Now, our function needs some arguments. Remember, this is a function, so I use the keyword function. Now here in brackets, I need to put the arguments of my functions. Now let's have here the number of years is 30, but let's have this flexible. Let's call it an argument that by default would be 30. And what other things we need? Well, we need the returns here. The expected return, let's just call it mu. By default, we can have it 3%, but then we can, when we call the function, we can decide whatever is the expected return. Let's have again the other parameter of the normal, let's call it sig here for sigma, the standard deviation. Let's have it by default being 0.05. And then do I need another argument? Well, again, to make this flexible, why not have the amount invested to be another parameter, another argument that the user might change? Okay, so in our problem, this was 1,000, but maybe someone wants to try for a different number. So let's add this as well as an argument. Now, this is a function. It takes, okay, so it takes those arguments and it's going to return the result we want, which is the random value of the accumulated wealth under the investment strategy that we've explained. Okay, how to do this? One key element is that, of course, we need to generate the random returns over n years, okay, 30 years. Okay, so that's probably a good place to start. So I'm going to generate a vector of those 30 returns, okay, or n returns in general. I'm going to call this factor. I can use my normal random variable, sorry, my rnorm command, which generates normal random variables. Now here, maybe a source of possible confusion, rnorm, the first argument is called n, okay? But I want n, the argument of rnorm, to be my n here, okay? The argument that I've also named n, okay? I've done that on purpose just to explain to you this possible source of confusion. So here I might write n equals n, but this, what's the meaning of this? It means the argument called n of the rnorm function, I want it to be equal to my n, which is the value of my function. Okay, the value of the argument called n of my function. Okay, so yeah, so n equals n, argument of rnorm is my n over here, which by default would be 30, but can be anything else. Okay, same thing here. Rnorm has an argument called mean for the mean. Here for me, I would like this to be mu, of course. And rnorm has an argument called, I believe it's SD for standard deviation. I always forget. Let's double check with our help here. Yes, it's SD. SD, the argument of the rnorm function, I wanted this to be the value of I've inputted when I use the function, which is sig. Okay, and that's it. Now, this rnorm would, of course, generate random returns with this mean and this standard deviation. What I actually want, what's easier to work with, is 1 plus the returns, because that's the accumulation factor. Okay, so then I'm just going to put +1 here. And this node would generate a vector of those normal with the added +1. Okay, let's just try it with specific values, 30 here, and a mean of whatever, and a standard deviation of whatever. If I do that, you see it's going to be a return around 10%, but +1. Okay, and then okay, well, here I've put a huge standard deviation. So let's put a smaller standard deviation. Okay, so then yes, it's going to be around 1.10, but there's random variations. Okay, that's a good first step. This would be generating those 1 plus returns. Now, what is slightly more complicated here is that each payment of 1,000 accumulates of some number of those factors, but of course the very first will accumulate of 30 random factors, and the second one will accumulate of 29, and the very last one accumulates of just 1. So how can we do this? Accumulate each thousands by the appropriate number of factors. We can probably do that with a loop. Maybe there's other ways, but I think a for loop is a good solution. So I'm going to do that, and I'm going to actually, maybe it's good to understand what we're trying to do before actually doing it in R. So let me take a second to go back to the PDF file and just explain what I'm going to do in R. So I should share the right thing. Okay, so the point is just this. Whoops. The very last payment, okay, the one happening here, just needs to accumulate of one factor. Okay, so I just need to grab this one and multiply it by one factor. Okay, and this is why I've named them kind of backwards. Okay, that it doesn't really matter, but I think it's slightly easier to understand if I name this one factor 1. Okay, this 1000 I need to multiply by factor 1, and factor here, remember, it's the full accumulation, meaning it's 1 plus a random return. Okay, for asset A or asset B. Okay, let's say A here. So this 1000 I need to multiply by just one time, one factor. But of course, this one is going to accumulate of 2 random factors. So this one would need to be multiplied by this one and this one. Okay, so what I'm going to do now in R is that I'm going to create new variables that's going to be the right accumulation for different payments, meaning the first one will be just this, but then the second one will be factor 2 times factor 1. And then, of course, the next one will be factor 3 times factor 2 times factor 1, because this thing here, the multiplication of those 3, would be the right accumulation factor that I need to use when I multiply by this payment of 1000 that happens at time 27, and so on. We kind of work our way backwards because the last one is the more like complex one that I need to multiply by the whole 30 accumulation factors. Okay, hope that kind of makes sense. Now let's just do that in R. Okay, so here I'm going to define those new accumulated factors that I'm just going to call them ACFAC. You could find a better name if you have one. This is again going to be a vector. Now I'm going to declare it to be empty, as I did in a previous video. For now, it's just it's a vector, but it's empty. And then I can iteratively add values to it. Now, the very first one, okay, what I called factor 1, sorry, well, the very first one would be just factor 1, okay? The accumulation of 1 year of a random return, okay? So the very first one, so remember, this is a vector. So if I want to put in the first spot something, I can just access this by this notation square brackets of 1. Okay, this is then the first element in the vector. This would just be factor 1. Okay, the first element in this vector called factor. Okay, that's all good. But now I've declared the first one, and then from there I can use a loop and declare all of them. Okay, a for loop. Yes. Okay, so I would do that for, remember the syntax, for I, the index. Now it's gonna run, because I already created manually the first one. I can go from 2 to the end of my vector. Here, remember, the vector is of size n in general. So I'm going to run from I, oh, sorry, I forgot, for I in 2 to n. Then I'm going to do something. Now, the second accumulation factor should be the multiplication of factor 1 times factor 2, okay? So let's just do that. But then it's going to be always the same pattern, because accumulation factor 3 would then be accumulation factor 2 time factor 3. Okay, if I go back to the, let me go back just for a second to my file. Okay, accumulation factor, what I call accumulation factor here 2, I would need to take factor 2 times factor 1, but factor 1 is also accumulation factor 1. Okay, so I take factor 2 times accumulation factor 1. Now, accumulation factor 3, okay, the multiplication of the first 3, I could just grab accumulation factor 2, which is already the multiplication of the first 2, times factor 3. But you see, it's always the same pattern. It's always the same pattern. Let's go back. Okay, it's always the same pattern. It's always accumulation factor I is the accumulation factor before, okay, accumulation factor, sorry, it's not called accumulation factor, it's called accumulation fac, okay, from before, I minus 1, but times the new or newest factor, okay, so factor here, I, okay. again, just take a second, pause, and make sure you understand on the timeline, why is it accumulation factor I minus 1 times factor I? And remember, factor is this vector over here, okay? And that's it, okay? Well, that's a slightly complex, but once you've done this, then you've done everything, because again, this for loop will run. The first one will create accumulation factor 2 based on accumulation factor 1 that already exists, because I've defined it here. Okay, I needed to define the first manually for this to work. And then that's it. Then accumulation factor 3 will depend on accumulation factor 2, which exists, times the factor 2, and so on. And the very last one will be the multiplication or the product of all of the things called factor. Okay, I hope that kind of makes sense. And here we're pretty much done. The only thing is that now we have done the hard part. We have found all of the multiplication factors, okay? But now we just need to multiply 1,000 times each of them, okay? Because this 1,000 needs to be multiplied by accumulation factor 1, this 1,000 needs to be multiplied by accumulation factor 2, and etc. But this we can do in one command in R. So let's do it. Sorry, I thought I was sharing the PDF, but I think it's okay. I don't think it matters too much. Okay, back. Yeah, it's always confusing. What am I sharing? Yeah, okay, I'm sharing R. That's fine. I just need to find the sum of all the 1,000 multiplied by all the accumulation factors. Okay, but this you can do in just one command. I'm gonna call it total accumulation, and then I'm gonna return it. But just to split this in 2 steps, I want to find it's just the sum product of accumulation factor with 1,000, but 1,030 times. Okay, so how can I generate a vector with 1,030 times? That's pretty easy. You can just use this function rep 1,000 and then 30. Okay, so that generates you a vector with the value 1,030 times. So let's do that. But here, remember, it's slightly more general. So I have n periods and an amount 100. So I'm going to use rep amount and then n. Now this is the vector. Now I multiply it by the accumulation factors. Okay, I multiply it by fact. Now this multiplication of vectors in R works element by element. Element by element, meaning, let's do a simple example here. If I multiply the vector 1, 2, 3, 4 times the vector, say 1, 5, 10, 15, it's going to multiply this times this, this times this, this times this, this times this. Okay, it's going to return a vector of 4. Okay, so you see element, this one times this one by element, this one times this one, etc. So this gives me really what I want, because it's 1,000 times accumulation factor 1, 1,000 times accumulation factor 2. So this would generate the vector of all the accumulated value of the single 1,000. So at the end, I want to sum all of them. I want to sum all of them. So I'm going to take sum like this. Okay, that's exactly what I want. Now the last step is just to return what I want, which is what I've called total accumulation. And this should work. Okay, this should work. Let's try. So here I declare the function. Now R knows that this function exists, and now I can use it. Okay, I can use accumulation value. Remember, here all of the arguments have a default value. So if I just do this, it's going to call this function with all the default arguments, which in this case correspond to asset A. And you see, it's a random value. Okay, if I do it again, I get a different result, different result, different result. But you see, it seems to have worked because I expect a value around 49K. If you go back to the tutorial, where is the tutorial? Theoretically, we know the theoretical value of the expectation. In the case of asset A, it's 49K. Okay. In the case of asset B, let's try it again, it's a bit less than 70K. So if I go back to R, you will see that, okay, those values, okay, they vary a lot, but they do seem to be around something 50K. Let's just try for asset B, which had a mean of 0.05 and a standard deviation of 0.1. This one should be more close to well, you see it's very variable. Okay, so it's hard to say where is the mean, because I'm doing that many times. But now we're not done, because we can do it one time, but now we want to do 1,000 simulations of, or 10,000 simulations of this situation. So we can do that in a loop. Okay, we can do that in a loop, another loop. Okay, a for loop that's going to call our function many times. So let's do it. And again, let's do it in a function. Okay, because then we can call the function many times with different parameters change. Okay, so we could call this whatever, but I'm going to call this week 6 question 2 simulations. Okay, because this is exactly the question from the week 6 tutorial. Again, this is going to be a function, and a function is going to have the exact same arguments, because again, we want to be able to change the n and the mean and blah, blah, blah. But also it's going to have another argument, which is the number of simulations. Okay, so you would call the function with maybe 100 simulation and then 1,000 and then whatever. So I'm going to have an argument that's simply the number of simulation. Let's just call this n sim. Okay, and then sim maybe by default can be 1,000, and then n is the same thing as before. Mu is the same, and I also need the sigma. Okay, and an amount. Okay, and again, I'm doing this in a function, so then curly brackets, whatever's in the curly brackets are going to be my commands. Okay, we want to do this. We want to do what we just did to find the future value after 30 years, but we want to do this n sim times. So we can place our results in a vector of size n sim. As I've done a few times now, I'm going to declare just an empty vector. Okay, I'm going to call it S, because capital S is a letter we've used many times to mean the accumulated value. I declare a null vector here, but now I'm going to update it with values that I create. And this really is easy. I'm going to use a loop, for loop. Again, my index, let's change a letter just for fun. Or yes, we're having a lot of fun. For k in 1, 2, n sim, because I want to do the exact same thing n sim times. What I'm doing is I'm just going to place an si. So the ith element of this vector will just be the result of one call to this function I've created here. Now, I've created this function. Okay, as soon as I've run it in my R console, now R knows this function exists and can use it. So I can absolutely use it inside another function. So I'm using a function that I've created inside of another function that I've created. Whoa, okay, mind-blowing. Okay, so yes, I'm allowed to use the function I just created, which is called accumulated value, inside this new function I'm creating, which is called week 6 Q2 blah blah blah. Now accumulated value, I need to give it arguments. But now this is again the slightly confusing thing, which is that, okay, the value n of accumulated value is this n that I have in my new function week 6. Okay, meaning accumulated value over here already has an argument called n. So what is the value of this argument? It is just whatever n is here, but it's also called n. So I'm going to say n equals n. I'm sorry, this is slightly confusing, but it is what it is. I could have avoided this by giving all those things different names. Maybe that would have been slightly more elegant, but maybe it's good that you're aware of this thing, because it happens quite a lot that arguments might have the same names. But anyway, mu is also mu, and sig is also sig, and amount is also amount. Okay. And then I think that's it, because then we have our S. We create n sim times the final value. Now I just want to display the results. And in the tutorial problem, they ask you for the mean, for the standard deviation, and for some probabilities that S is bigger or smaller than some values. So let's do that. I'm going to call this my results, and results will be a vector, because there's a few different things I want. I want the mean of S. I want the standard, yes, I want the standard deviation of S. And I also want the, let's just go back to the tutorial for a second. We're asking you for those things, the probability that S is smaller than 40K and bigger than 70K. Okay, so now I have a vector of simulated S values. I can find the approximate probability that it's below a certain number or higher than another number. Let's do that. Okay, how can you do that in R? Well, it's pretty simple. If you type any vector, let's say a vector of 2, 3, 4, 5, 6, whatever, if I use logical operator like smaller than say 4, what's going to happen? It's going to do element by element. Is 2 smaller than 4? Yes. Is 3 smaller than 4? Yes. Is 4 smaller than 4? Strictly, no, it's false. And then of course 5 and 6 are both false. Okay, so I can use this behavior for the following. Is S, remember, is a vector, but is S smaller than, if I want to find the probability that's smaller than 4e, okay, so this would be a vector of true and false. But if I sum, a vector of true and true, it's going to give me 2, because as in Excel, true, when you manipulate it with mathematical operation, true is interpreted as 1 and false is interpreted as 0. So what's the sum of true and true is 2. What's the sum of true and false? It's 1. What's the sum of false and false? It should be 0, and so on. So how many times was S smaller than 40? If I sum, this, you see it's going to sum how many times this statement was true, but that's exactly an approximation of the probability the statement is true if I divide by the total number of times. Okay, so how many simulation values do I have in total? Otherwise, what's the size of the vector S? Well, it's n sim. So if I count here, this is counting how many times S was smaller than 40. If I divide it by the total number of trials, it's going to give me an approximation of the probability S is smaller than 40. Okay, hopefully that makes sense. And I also want to find the probability it's bigger than 70K. And so exactly the same trick. Okay, count how many times it's bigger than 70K, divide by how many times I've simulated S. That gives me the approximate probability. Those are my results. Like, just lastly, maybe that's not entirely necessary, but let's name our results. Okay, so you can do this with names of results. This is just because this would be a vector of numbers, but if you want to give it meaningful names so that the user knows what is what, might be good to give appropriate names. So here, I'm just gonna give it the vector of meaningful names. Let's just call it mean. The first one is the mean. The second one, this one is the standard deviation. It's called standard dev. And then the other ones are probabilities. Okay, so probability that S smaller than 40 pays. And the last one, whoops, probability that, okay, S is bigger than 70. Okay, now that should be good. And then I'm gonna return result, and I'll be done. I think, if I haven't made any mistakes. It's always a risk of doing that in real time. Okay, now I just declared this function. Let's try it. Okay, let's try it. Okay, here again, if I don't put any arguments, it's just going to use the default one, which is what I want in this problem for asset A. No, of course I would make a mistake. Okay, SIF doesn't exist. Of course it doesn't. You probably spotted this mistake that I've made way before, and you were waiting for me to fail. Okay, that should work now. We're gonna recall the function, redefine it with the corrected typo. Now, why? Of course I would make many mistakes. Yes, it's not I, it's K. You see, I get punished for changing I to K. Okay, any more mistake? Usually, what's the saying? A third time is a charm. Yes, that seems to work. Okay, so for asset A, you see the mean is very close to the theoretical mean. Then the deviation is this. Probability to be smaller than 40K is this, and probability to be bigger than 70K is this. Now let's just jump to Excel and see if those numbers match. So try to memorize those numbers and see if they're close to what we had gotten in the Excel simulations. Okay, so this would be the solution to this problem Q2 for asset A. Yes. So again, of course, those numbers are random. If I recompute, they're going to change a bit. But yes, we're around 49K, 8K something for the standard deviation, and then 12 something and close to 1% for the probably to be bigger than this. Okay, I think that matches pretty well what we had approximately, because this is still the result of random simulation of only 1,000 simulations, right? So, and let's just check in Excel again. When we had 5% for asset B and 10% for asset, sorry, for the sigma, now we get 70K. Standard deviation is much bigger, but then the probability here is actually smaller, and the probability to be bigger than 70K is pretty big. So 8%, 42%. Let's memorize this: 8%, 42% in Excel, and go back to R. How many times do I jump back and forth here? Okay, if again, now the magic is that I can, of course, use my function and call it for whatever parameters I like. So asset B is this. Okay, and again, yeah, so more closer to 70K and 26K, and here we had 12% and we had 40%, I think, or I forget, 42%. Okay, relatively close, but of course, again, I'm doing this for just 1,000 simulation. But here, I guess a strength of R is that you can increase the number of simulation. Should work relatively well and quickly for even 100,000 simulation. Let's try. Okay, it's taking a second. Okay, it took 1 or 2 seconds, but still, now we get, again, this number, the theoretical value was, I believe, I forget, 79.7. Yeah, 69.760 was the theoretical value. Pretty close, okay? Because now I have a 100,000 simulation. Okay, I believe I probably gonna stop here. Actually, okay, a little bonus. 2 little bonus, actually. So I've solved the problem. We've solved the problem, okay? There is one thing. I suppose it's slightly annoying to have those values, those n equals n, mu equals mu. You could have done something a bit interesting. You could have declared this function. Well, actually, you need to declare the function. Okay, I'm misspeaking now. You could have declared this function inside this function. That could work, but in fact, let's not do that. I think it's not that. In fact, what works here, I don't actually need to specify the arguments, right? Because sorry if I'm thinking in real time, but n exists here. So no, that's not going to work, because yeah, you need, let's do it. Okay, you need to declare this function. You need to declare this function, cumulative value, inside the other function. So let's do that. Okay. Now, here, I'm declaring accumulated value inside the bigger function, which is the final result I want. Okay, let's explain why would I do this. Now, accumulated value is still a function, but it doesn't need any arguments, because all those things, n, mu, sigma, amount, they already exist. They're already declared here. So when this function is called and it goes here, there's an n here, but that's fine. The n exists. It's already been defined. Okay. So again, that's not massively important, I guess, but it's slightly more elegant. If I declare accumulated value inside the function, so a function declared inside the function, mind blown. That's possible. Now I don't have the confusion really of any sort, because this function exists. Okay, s is as before. Okay, just declaring a vector. And by the way, it's a good practice to comment your code here. I haven't really done it because I had bigger fish to fry, I suppose. But in general, with this thing hashtag, you can. So hashtag means this is not a command R is going to read. It's just to help the reader or the programmer. Okay. Now we go here, and again, we can use accumulated value, and it's going to use accumulated values with those argument. Sorry. Yeah, it's going to use the accumulated value with n equals this, mu, and sigma as specified by the user here, here, and here, and here. And I believe that will work. That should work as a charm. Let's try. Oh, again, it's taking a second because I have a huge, okay, it gives me a very similar result. Again, it's not exactly the same because again, those are random simulations. Let's just try again without arguments, but that should work as well. But now without arguments, it would be the default values used, which are those of the asset A here. And yes, okay, closer to 40, was it 49K? Yeah, and yeah. Okay, one last thing. Okay, one last, again, pretty much a small thing. Whatever you declare inside a function doesn't exist outside the function, meaning that this object S, even if I've called a function and S is defined inside the function, in R, if I type S, it doesn't exist. Okay, object S not found. That is maybe something, maybe you want to access S, even if it's been declared inside the function, because you want to do other things with this S, which is a vector. So there's a trick. If you declare S in the following way, instead of just the regular assignment symbol, you declare assignment. So two times this bigger than symbol, I suppose. Well, I'm going to do it again here because again, I'm updating S. Now doing this will mean that S exists outside the function. So if I call it, I redefine the function, and now I call it again. Okay, I get some other values. But S exists. Okay, well, S is 1,000 values now, so okay, it exists. But now I can do fun things. I can do the histogram of S as before and see the shape, and I can manipulate the way I like. Okay, so now I have the histogram. Gray is slightly boring color, so let's use another color, maybe another of my favorite R colors, which is light golden rod. And whoops, there you have it. Okay, a nice histogram of the values of S. Okay, I know it was quite a lot and it's slightly tricky, all those things. If you have any questions, you can ask them on ed. And by the way, you can run R code in ed. Okay, maybe I should take a second to show you. Okay, so if I'm in ed, someone asked a question here. Let's say that I want to reply to their question by using R code for whatever reason. So is it? Yeah, code snippet here. So this is R code. So we can run whatever, all the things you just saw. I can find the result of R norm 10 times. And so yeah, you can, if you have questions about R, you can ask them in ed and even share a bit of code here that we can run and try to debug and things like that. Okay. Now I'm going to stop here. It was the very last R video, and also the very last programming video. And so yes, thank you so much for having followed me up to here. And I'll see you soon in another teaching activity, I suppose. Bye-bye for now.